Hello to everyone. Let's wait a little bit for people to join, and then we are going to start this webinar on HP 3D multi-jet fusion technology and its applications. Let's wait a little bit for people to join in, and soon we will be able to start. Okay, I think that we can start now. Welcome to everyone. My name is Gianni Cessel, and I am a member of the IT and a volunteer for the Barcelona local network. I organized this webinar to follow the spirit of the IT and especially to inform, inspire, and influence our community. We go to the agenda. There is a brief introduction, which I am already doing. The AIT is one of the world's leading professional society for engineers and the technical community. It provides global knowledge networks. HP Inc. is a worldwide company providing computer equipment and services. One of the products is developed is HP 3D multi-jet printers, a development which occurs in Barcelona and other sites in US. The overall meeting is going to divide it in two parts, where we will cover the technology first, and then a demo on the application and materials. Each of these two parts will be followed by Q&As, so that if you post your Q&As in the Q&A box of the Zoom meeting, I will read them out, and the speakers will be able to reply to them. As speakers, we have the Marc Jansat, who's R&D section manager at the HP Barcelona site. Apologies for Sasha de Peña, who was not able to join. And then we have Marta Tauler, who's a product marketing manager for the materials and application, and she's going to explain what are the materials and the applications for this particular technology. Without further delay, what I would like to do is to call on Marc Jansat, who's going to take over the presentation and explain the technology for this HP 3D multi-jet printers. Thank you, Marc. You can take over.
Hello, do you hear me? So welcome to the site where the MJF technology was invented. So around 2013, we took the large format printer, the upper part, we changed the bottom and we put a bed of powder, and we created the 3D printer technology that today is the leading technology of the 3D market right now. So my name is Marc Jansat. I'm a section manager in R&D. And now what we are going to present to you is where we are. Okay, so this site that created this technology, you're going to see how is it about. Okay, so now we are going to roll a video, so you'll have the chance to see where we are working right now.
There is a place where innovation lives, where hundreds of experts in 3D printing and digital manufacturing are developing advanced solutions to transform the way we think, design, and manufacture. A place with more than 150,000 square feet of cutting-edge innovation space, making it one of the largest and most advanced research and development centers in the world to date for digital manufacturing and next-generation technologies. Welcome to the home of the fourth industrial revolution. Welcome to the HP 3D Printing and Digital Manufacturing Center of Excellence.
So what you've seen is the new building, what we call Building 10. It's a luxury to be able to design not only the products, but the lab. So we call it Carpet Lab. It's 15,000 square meters. You see all the engineers working next to the machines that are doing testing 24 hours, 7 days a week. Okay, so it's in a very, few occasions in your life that you can create also your working environment, and this incentivizes all the creativity that's required to create a new technology that's going to roll the wall. Okay, so now what I'm going to start is to present the big modules of the technology. Okay, so we are going to start here. What you have, this is the printer. Okay. Okay, this module here is the printer. Here is where we are doing the layers of the powder. Here you have the top lamps, and here you see the carriage moving back and forth, and this is fed with this other module that it's called the build unit. It is the powder. So back down here is all the powder that's coming up on the sides up to this point with an Archimedes. This area here is distributing the particles in a way that you don't get segregation. It's very important that the particle size distribution is even in the whole distance. And then what we have is a recoater, is a roller that creates the layer of 80 microns, very flat with accuracies of microns every time. So from one side and from the other side to here. And then after the layer is created, then the carriage passes. And as you'll see now in a video, you'll get better understanding of how we decide where to fuse and where not to fuse. And then the third module is this module here. This module is to remove the parts from the powder. So at the end, you get the parts in a bed of powder, and you have to remove them. And also this module here sieve the powder and mixes with fresh powder. It's very important that we reuse 80% of the powder, so only 20% is new, and that's one of the reasons why we achieve the cost, the operating cost that we achieve. And finally, in order to speed up the whole system, we have this module here. Okay, we call it natural cooling unit. This is to free up your equipment, your assets. So with this, you can cool down your parts while you reuse the printer again and the processing station. Okay, so this is the four main modules. So the printer, the build unit, the processing station, and then the natural cooling unit. And now what we are going to do is we are going to roll a video, in a few seconds video, that we are going to explain the technology. You'll see how we have two agents, and we put a fusing agent where we want that part to be fused and create the part, and we have a detailing agent for to maintain the details where we need to maintain the details. And you'll see how the printer is doing the 80 microns layers, 100 micron layers, depending on the different operating settings that we have on the machine. So now we'll roll the video, and you'll have a much better understanding of what's going on, and then we'll discuss the advantages and the challenges that we have in the technology. Okay, so we have some technical problems that we are going to solve soon. Yeah, yeah. That's what I do. So in the video is about the printer. Okay, so what you'll see here is going to be what happens in this area. Up here, you see there is two main heater systems. There is the fusing lamps that are moving on the carriage, plus the top lamps that keep the powder at the right temperature. Plus this is a Heyman. It's a sensor that it's measuring real time what's the temperature on the top layer at all the times. Okay, so with this, we're able to close the loop and understand what's the temperature that we have on the fusing piece and what we have on the white piece, which is quite critical. Okay, we are keeping the white in a temperature that's okay. Now you'll see the video and I'll explain that later. See?
Produce truly functional parts, it's important. To produce truly functional parts, it's important to ensure that the material has been properly fused and that part edges are smooth and well-defined. To achieve part quality at speed, HP invented a multi-agent printing process. In this process, a fusing agent is applied on a material layer where the particles are meant to fuse together. A detailing agent is applied to modify fusing and create fine detail and smooth surfaces. The area is exposed to energy, and reactions between the agents and the material cause the material to selectively fuse together to form the part. The fusing process requires accurate temperature control across the entire material layer.
Okay, so what you've seen is kind of the essence of the technology. Okay, so this technology is the best technology in the market today to scale into manufacturing. Why? Because we are 10 times faster, up to 10 times faster than any of the other additive manufacturing technologies. The reason is that we are reusing all the inkjet technology that we had at HP, so we can print regardless of the complexity the whole pass from one side to the other in about 7 seconds, 5 seconds, depending on the print mode we use. This is very different than the competition that they have to go and use a laser that's kind of following all the different content that needs to be printed. So, I mean, that's giving us the big advantage on the speed, which is one of the key things that we want to do. Second, we are providing the best quality. So other additive manufacturing technologies, they have the challenge of the detail. The fine detail is very difficult to contain the heat not to be conducted to the near other particles of powder. So with the detailing agent, what we are doing is stopping the fusing just at the right edge. And with this, we create the detail that's required and the sharp edges and the small holes that it's really what's making our technology the best. And third is the cost. Okay, so you need the productivity, the quality, and the cost in order to get there. So the break-even depends on how many can you put on the whole bucket, but we can compete up to 100,000 if the part is very small. If the part is getting bigger, you have the break-even point with injection molding around 10,000, few thousand parts. Okay, so with this, this is how the technology works. Of course, any technology requires a lot of fine engineering in order for that to work. I'm going to show you some of the challenges that we have. This is at the end is a thermal machine where we have to control the temperatures to a few degrees. So if you shift 2, 3, 5 degrees up or down, you start having fusing problems in the parts. And I'm going to show you a couple of part quality issues that we are facing. Okay, so the first one is this one. This is a dental aligner that is a technology that is used very successfully in the market. As you can see here, if it's focusing. Okay, so here you see what we call elephant skin. It's changing the quality of the surface. This type of phenomena happens when there is a drop on temperature of a few degrees. So 3, 4, depending on the material, is more or less sensible to this type of changes in temperature. So if it's too cold in a given region of the bed, then you have this type of problems. The opposite is this one, okay? So this is showing the opposite. If you have the bed or part of the bed or the part is too massive or whatever, you get what we call thermal bleed. This part here is powder that is being fused, fully fused by the heat that's coming out of the part. So it is powder that cannot be removed. Usually just blowing, the powder kind of blows away. But this one is fully attached here and you cannot remove it. So what we are saying here is that we are having a very tight thermal control of the machine using the thermal camera on top that I was showing you before, Rita and figure. So here is the thermal camera that you see. Okay, so in here, that little here is an infrared camera that's looking all the time at the temperatures that we have on the bed, and we are able to close what's the actual temperature. Plus, we have another big important element is the data. Okay, so data is very important. We are all the time collecting data. We are printing this type of segments or test structures that we use. And what you'll see now is a full one. So this is the full bed. Now I'm going to come here. Okay, so this is the dimension that we can print. This is full of these little pyramids or test structures. Okay, so all of these we are printing all the time, trying to understand what is the actual variability and repeatability that we obtain with these machines. Okay, so this is, the 5200 series, which are the ones that you have on the back, are the only ones that can claim CPs and CPKs in the market, similar to what injection molding is capable of doing. Okay, so we're going to show now a video on metrology that's key for us in order to get the data, and then I'll explain what we do with all that data later. Yeah, we'll try to roll the video this time. Okay. Okay, so you've seen the metrology lab where we have a lot of dimensional capabilities plus mechanical studies. So it's both. We have to look, a good part requires the good dimensions, it requires the good mechanical properties, and it requires the nice look and feel. So we have everything connected, okay? We have a database where we put the job that we are putting into the machine. Then we have the telemetry of the machines continuously monitoring into the cloud. We have a lab of more than 40 printers always printing, 100 printers overall in the whole building. Then we go to metrology, we connect that data into that, and then we apply this machine learning neuronal networks in order to get insights to improve what's going on the parts. We recently discovered a problem that was happening in the recently released PP material, where we had 3-5 degrees difference between two sensors, and that was causing some image quality problems, part quality problems. That we corrected that, and now that defect is not even longer in the field. So it's really a technique that we use, and it's a new engineering method that is helping us to really go further and advance quicker in the technology development. Okay, so I think that now we are at the time for questions and answers. So if you had any question, please feel free. So I think Gianni will read the questions.
Yes.
So, Gianni.
Hello, Mark. There is one question for you. The question asks whether this technology is only for plastic or is it also for metallic? So can you expand a little bit on this question,
yes,
please?
So what I describe is mostly on plastics. We are also working here in Barcelona on what we call metal jet technology. This is based on the same technology fundamentals, but it's different in the sense that it's got to go to, it uses the same principles, but then you have to go through sintering. So metal jet is a technology that we have now in some key customers. We are learning at. It's not yet in wide availability, but it will be as soon as the technology is ready for wide scale.
Thank you, Mark. Then I would like to ask another question, and it is whether these parts can be colored or can be somehow polished with cosmetics and varnish. Is there any coloring of these parts possible or not?
So we have a machine that's called the 500-800 that they have some color. So the printer itself colors the skin outside. That's one possible solution. Second, you can get through colors through post-processing. So there is a lot of post-processing available in the market. You can do some chemical polish to the parts to reduce the roughness, and then you can apply metallization, you can apply paintings, you can apply many finishing that are common even in the injection molding industry. So that's not something that's actually unique to us, and then you can get to any finishing we want. So we've been printing these, and they have in parts in cars, in the external side of the car. So you can do anything once this part is finished, and you polish it a little bit, and then from there on you can use any technology that is available in the market.
Fantastic, Mark. This is all for the moment. So thank you very much for your presentation and for sharing information on this technology with us. What I would like now is to move on to the next part of the webinar, which is the part where Maria Tauler is going to share with us the applications and the material. So I'd like to switch over now to Maria. Okay. Let me see if I can do it. Maria Tauler is a product marketing manager. She is responsible to communicate the advantages of the application and the material. And we are now ready to go to another part of the HP building where she's going to show the properties and the applications where this technology has been used. Maria, whenever you are ready, you can take over the presentation. Let me see. Maria. Here she is.
Hello.
Welcome.
Can you hear me?
Yes, of course.
Yes.
Please go on.
Okay, good. Thank you. So my name is Maria Tauler, and I work as a product manager in 3D printing. So what I will be doing today is explaining the materials that work with our technology that Mark just explained, and also link it with the applications that this material will enable. So if we start with with the type of plastics that we can produce with our technologies. There is the typical list of polymers, a way to classify it. And can we see the slides? One sec. Ah, yeah, true. Sorry. Okay. Yes, perfect. So I wanted to start first with the classification of materials. You may be familiar with that already. It's not something about 3D printing. It's a general way of classifying the materials. So which are the plastics that we can process with our technology? And what we can do is the thermoplastic semicrystallines and also the elastomers thermoplastics. So these are the materials that today multi-jet fusion can produce. And from these materials, there are several materials. There are a lot of different materials, but the ones that we are today working with our printers are in one hand the rigid materials. We are working today with several polyamides. We have the polyamide 11, polyamide 12, polyamide 12 with glass beads, and the polypropylene material. And then on the elastomeric side, we have also 3 elastomeric materials today. We have the Lubrizol TPU, we have a BSF TPU, and a TPA material. What I will be doing now is for each of the materials, explaining what are the key advantages of this material, which are the key aspects that they will bring, and also which are the type of applications that this material can enable. And we will see several examples here in the table. So the first material is the PA12 material. PA12 is the first material that we introduced the printer with, and it's actually the main material in 3D printing market. This is different from other technologies. In injection molding, the polyamide 12, it's not very used today. There are other materials that are much more used, like a polypropylene material, for example. But in 3D printing, this is different. PA12, it's one of the materials that it's most used. This material, it's a very strong material. It's a very functional, and what we have with this material is a very robust solution. Well, almost, from our install base, most of the customers are printing PA12. At least it's a material that they started with. Now some of them are moving to other materials to expand their applications possibilities, but also it's the most used one. And what this material will bring also, it's a very low cost per part, thanks to the high reusability that it has. And this is different also from other 3D printing technologies, where, for example, the reusability percentages, the ability to reuse the material, it's around 50%, whereas in our case, it's 80%. So that gives a cost advantage to us. Which are the key examples for this material? The main application, the key application that we've had so far, it's the dental application. And this is the one that we see here. No, but I can, sorry. It's not working now to pass the slide. Now, okay. So this is the dental application. Here we have several customers. The one that you're seeing now in the slides, it's the biggest one that we have today, that have several of our printers. They have around 70 printers in their factory. And here you can see the entire bucket of the dental molds. They have, here there are more than 350 parts just printed at once. And here what they are doing is customizing the dental molds to have afterwards the Invisaligns. Maybe I can go closer so you can see how packed the parts are. Okay, here we are sharing it in different levels, but in reality you wouldn't have these support structures. It's just the powder itself that would be the support. So what they are doing is customizing these dental molds for each patient. And what they are doing is also completely disrupting the market, and they are changing the way you go to the dentist, and you would usually have this orthodontist. And they are doing everything remote so that you don't have to go to the dentist every time you need a change in your orthodontist. You can do it remote with a 3D scanner, and then you would send the scan to them, and with the software they would produce these molds to send you your Invisaligns. Okay, so this is one of our key applications. Then with PA12, we also have different markets. For example, we have here these glasses. You can see that here these parts are I'm sorry, we will put now the camera so that you can better see it. This type of parts. These are glasses. I don't know if you can see it, but the finishing looks like a normal glasses. Normal, I mean like produced in traditional methods. But here the main advantage is not also that you can do different geometries and innovate with the design, as you can see here that they are doing, but also that you can customize the glasses to make a perfect fit with your face. And here, for example, what some customers are doing are in the optica shop that you would go, you have a face scanner, and then they scan your face and they will produce the glasses that are perfect for you. So this is also a very new application. And then on PA12, the other types of parts that we have a lot of customers producing are industrial parts. We have several examples, and we have, for example, type of parts that are going from metals to plastics. And here, for example, we have this part. It's a part from a machine. And before it was CNC machine with metal, and there are several. It was produced with several parts. Sorry, one phone. It was produced with several parts, several screws, so the assembly time was very long. So what they did, this company is completely changed the way of manufacturing, and they are now producing it with 3D printing in just one piece. So you can imagine that the assembly time was reduced a lot, but not only that, that also the weight, which was also important for the type of machine, was reduced by 95%. And coming together with that, the cost was also reduced by 90%. So this is a very good example of moving from metal to plastics, where you have the same functionality, but you can reduce a lot the cost. And then also this example that we will see a video. This is a pneumatic system, okay? You can see here the part was designed to strengthen in some parts and have flexibility and mobility in other parts. So this now in the video, you will see the type of movement that it does, but it was also optimized for 3D printing and this part had to withstand 1 million cycles, which we accomplished with this design. You can see how with the pneumatic system, thanks that our parts are fluid tight, airtight, here you can have this type of movement. And this part was to move parts around a production line. And what I was saying, yeah, they had to have a part that withstand 1 million cycles. And with this redesigned part, this is what we accomplished. Okay. So these are some of the main examples of PA12. Now let's move to PA11, which is the second material that we introduced with our machine. PA11, it's similar to PA12 in terms of strength and rigidity. So it's also a polyamide, but what it has different from PA12, it's the flexibility, the ductility of the material. It has a higher elongation at break, and also it has higher impact resistance. For that reason, the type of applications that we are focusing with this material are parts that have clips, that have snap fits that require flexibility, or also, for example, orthotic parts like insoles that you also need some fatigue and movement, dynamic movement. So the key example for the PA11 as a use case, it's the orthotics parts. It's where we are having more examples. If we can move to the next slide, because it's, yeah, we have this type of parts that we will see in the, yes, that we see in the slide. You here need some material that has this flexibility. That PA12, in some cases it can work, but with PA11 you have this extra durability that it's what you want. With this type of parts also, the key advantage of 3D printing is to be able to customize it in a very fast and efficient way. Before, a lot of these parts were produced with CNC, in a lot of cases with polypropylene material, but with CNC you have a lot of waste material that with 3D printing you do not have. And also the ability to customize it and have the softwares to scan the food and everything is also that we are doing end-to-end. So our customers are doing end-to-end solutions for this type of parts. And here, if we put the camera again one sec, you will see what I'm talking about on the flexibility. So this is the type of movement that you need for this material. This was printed super thin, you can see, and thanks to the properties of the material, you can withstand a lot of cycles like this. So these are This is, for example, an orthotic DAFO part. And then with P11 also we have some industrial cases. Here we have an example of Bowman. I'm going to take the part, it's quite heavy, but I'll try. This is a bearing cage. The camera, please. Yeah. So I don't know if you can see, this is a bearing system, and Bowman is a bearing producer. And what they were doing is producing these cages before with metal, here again with aluminum. And what they thought is, why not 3D printing it? And actually they realized that they could do it in plastic. Metal was not needed in a lot of cases, and they completely optimized the design to increase the load capacity. How did they increase the load capacity? By being able to put more bearings with the same type and with the same size of cage. And this was thanks to the design that they could do in 3D printing. This is also a high production application that it's, and P11 was the material chosen here as well, because you have some clips here that you need some flexibility to assembly and disassembly. And then another type of example, it's a drone. Here you can see it. This drone was done with P11 because you need impact resistance, so that if it falls, it doesn't break, of course. But also you can see here that they completely redesigned this part so that it's super light, but at the same time it's very strong. It was critical for a drone because the lightweight is one of the most important aspects. And then another new application, and this is very recent, and this will be familiar to you. This is a nasal swab. This is also one of the applications that we've been producing this last year. It's very small. I don't know if you can really see the level of detail, but it's this was thanks to 3D printing, because you needed the fast time to part, because as you know, a lot of medical manufacturers didn't have time to get to the demand that was needed at that time. So that's why 3D printing was starting to be an option for this type of parts. And then now let's move to the next material, so PA12 glass beads. If we go back to the slides, we will see some details. PA12 glass beads it's based on the PA12 material, the same that we were explaining before, but it has a reinforcement of 30% glass beads. What the glass beads do is they give a reinforcement on the rigidity of the parts. So what it will differ from PA12, this material, it's mainly the rigidity, and also the dimensional stability, which is very important. Dimensional stability, it's critical in 3D printing, because in a lot of cases, if you want to produce flat parts, you may have warpage, and glass beads will help you reduce that. Thanks to the glass beads, you don't have as much warpage. So this material, it's true that it's not super not a lot of our customers have it yet, so it doesn't have the success that PA12, for example, or PA11 has. But for some specific applications like this type of enclosures that you have flat parts, it's ideal. Okay. And then we have the last rigid material that we have today is the polypropylene material. Here polypropylene, it's very well known in the injection molding market, and here it's not like PA12 that in injection molding it's not very used. Polypropylene, everybody knows about this material. In automotive they use it a lot, in consumer goods they use it a lot, so it's everywhere. But also there are a lot of different polypropylenes in traditional methods. So we decided to introduce this material because we thought that a lot of traditional companies that were using this material would be able to adapt easier in additive manufacturing if it was the same material that they are used to. And what we are seeing is that one of the main applications today is the functional prototyping and the bridge production, these first samples that you would do to test a product in the market. Here you have, for example, some of the examples we will be sharing. This is a manifold produced in this polypropylene material. Okay, here the customers, what they are doing is doing this functional prototyping with PP, and then the final part is with PP. But the advantage is that they can use the same type of welding, for example, welding methods, processing methods, than with the final part. Also, some of the key advantages of polypropylene are the chemical resistance, the welding, as I said, and the low moisture absorption. That's why also the any type of part like tubes, fluid systems are some of the key applications for polypropylene, and not only prototyping, but we are starting to see more projects on final part production. And we have the example of Vextol that we are seeing now in the slide. And this is a company, it's a part provider that they are working mainly for automotive companies. And what they were doing is they were one of the first customers to start printing with polypropylene. And what they are using it for is first for the functional prototyping for the OEM customers. And then be able to produce with the same material base than the final part, but also the bridge production. And this was thanks that our PP material is the same material base, so they can use the same welding methods that they were using with injection molding and be able to weld it also with injection molding PP. So that was one of the key advantages. Okay. So this was for the rigid materials. Now we will move to a complete different type of applications. And this is for the elastomeric materials. So for the elastomeric materials, we have, we were showing before, we have 3 different materials. And here you will see that the name, it's not HP name, we could say. We have BSF, we have Lubrizol, and we have Evonik. And this is because these materials are certified, so that these companies produce the materials to work with our printers. But it's a different method that we have. So if we have first the BSF material, this is a flexible TPU. It's a 88 Shore. You will see all our TPUs are quite hard, are from 85 to 95 Shore. It's very hard for us to produce lower shore materials, TPUs. So this TPU, the BSF TPU, it's 88 Shore. What it has, I will be sharing a little bit the advantages versus the others. In reality, they are quite similar, all of them, but for some specific applications, one may work better than the other. The BSF, for example, what it has, it's a very good level of detail, which is very hard usually with elastomeric materials. But if you want to do textures or small holes, this material it's very good. What it also has is very good UV and hydrolysis resistance. We have tested, BSF tested that, and also that was a very good advantage. Then if we move to the next slide, we have the Lubrizol TPU. What I was saying, very similar. What it has, this material, is that it has, it's harder, it's 95 Shore. But also one of the key properties that this TPU has, apart from the flexibility overall, it's a higher resistance to high temperatures, higher than with other elastomeric materials, and in some cases actually higher than with polyamides. And also what one of the key advantages with the Lubrizol TPU is the ability to clean it very well. And this is actually something that I didn't say with the other TPU, but in general, elastomeric materials are harder to clean. To do the unpacking after the printing, you have all the parts, as Mark was explaining, with the powder, and you need to clean them. So with elastomeric materials, usually the powder, it's more sticky. So then with Lubrizol, what we have is a key advantage here because it's less sticky and then it's easier to clean the parts. And then if we go to the next slide, we have the TPA. This is the last elastomeric material that we introduced. It was actually on autumn that we introduced this material. And one of the key advantages is that this material is a flexible polyamide. And this is also a good thing that the market is receiving because they are very used to work with polyamides in 3D printing. So to be able to say this is a flexible polyamide, it will have a lot of properties that are going to be similar with your polyamide. This has also resonated a lot. Also, at this material, one of the key properties that the TPA material has, it's the rebound resilience, the energy return that you would say, for example, in footwear that you would need for a sole, no, that you have this energy return. With this material, it's super good. Also, this is injection molding, but we are seeing that in 3D printing we can also have this advantage in the property. So now I wanted to show, if we go back to the camera, some of examples of these elastomeric materials. So we have, for example, this part, and this is an industrial part. You can see it here. This is from a company called Vestas. They are a wind turbine manufacturer, and they needed a part to clip the blades when they assembly and disassembly the parts, and they had to rotate it. So they designed this part that they needed somehow that it was rigid here in this part where you would put the blade, but also some flexibility on this part here. Okay, you can see here it's more flexible. So the time to part was critical, so that's why they chose 3D, but also the production runs were very low because it was when they needed to assemble some of the turbines. So that's why they needed somehow a fast turnaround, but also something that it was cost-wise, it made sense with low runs. So they produced this part. Then we have in consumer goods, another key application for elastomeric materials. It's all the sports protection. Here we have an example of a helmet. Okay, you can see here the lattice structures. Okay, this is it's a half helmet. It's an example, but here what it makes a lot of sense to produce it's this internal part. And this it's not about personalization like prosthetics. Maybe in the future it will be, but it's more improving the protection. And what we are doing is designing this type of internal structure so that you can improve the protection when you receive a shock. And for example, there are some type of lattices that when you receive an impact here, for example, you would have a rotational movement, and then your brain gets less damage. So these are the type of investigations that helmet manufacturers are doing. Then another example on industrial also, it's tubes, flexible tubes. Here, this is an example in automotive, for example, in prototyping, also in industrial machinery. And this part that is more black and it's like shiny, this is the finishing that it's chemical polish, the name, and it's a post-processing that you apply to the surface to make a look that it's more similar to the injection molding finishing. But it's not a cosmetic finishing, but it also for this type of tubes where you need a complete tightness, this type of process also improves a lot these properties. And then the last use case for elastomeric materials, it's this. This is in printed small, but this is a real example of a car seat. Okay, here you can see the type of lattices, also with different types of finishing. Here in gray, it's the raw part, how it comes from the printer. Here with the chemical polishing that we were also showing before. And here with the chemical polishing and coating. This is a coating that you can do in colors. This is actually also from BSF, and it's a spray flexible coating. This type of parts are, this is a project for luxury cars where they also wanted to do some different differentiation in the seats of the car. So they are designing this type of lattices to make this differentiation and improve the level of comfort on their cars. So it's also a very interesting project. And then the last thing that I wanted to share today, it's the examples that we have in the color printer. We have focused more on the production applications and the production machines, but we do also have a prototyping printer that it's a smaller printer that prints directly in white or color. Some of the examples of applications of these parts are, for example, here the jigs and fixtures. We were saying that with the production printer, you also have a lot of examples, but with color, you have an extra advantage, that is the ability to be able to put labels and mark the parts to have faster assemblies. Here, for example, you can see in the part, there are some labels, some marks in the part, but also these bezels, you can see here inside there are bezels with different colors. This was to reduce the mistakes when assembling and disassembling the parts in the production line, so that you know that the pink goes with the pink, the blue goes with the blue. And then another example of the color printer is these medical models, anatomical models. Okay, you can see here, this is quite impressive, the level of detail and that you can get. This is also quite big part. This is also super interesting for hospitals. The doctors use it for the surgeries to be able to plan in advance, especially when they have very complex surgeries that they need to know where the tumor is and how to go in and really plan the surgery. This they've seen that it helps a lot to reduce the time of planning and also reducing the mistakes on the surgery. And the time in surgery is super critical. So this also can collaborate a lot on reducing costs for hospitals. So this was all for the materials and applications. And I think now we have some time for questions.
Yes, Maria, this is Gianni, and I'm going to read a few questions that I've received.
Okay.
Here is the first one. The first one is about whether this technology or these machines are used in the airspace companies or in the airspace industry like Airbus.
Yeah, that's a very good question. It's true we have not talked today about aerospace, and it's because it's a very difficult market to go into, especially because of the regulations, also the type of materials that you need. As you can see today, the materials that we have are not reinforced materials, are not materials that are flame retardant, and these are the type of requirements that you have in aerospace. So that's why our penetration as of today has been very, very low. We've done some prototyping, but we don't have real use cases in aerospace yet. The only thing we have is the drone that we could say in aerospace.
Thank you, Maria. I'd like to go on with the next one, which is a question where the person would like to know whether there is any metal component or what is the speed of manufacture of metal components with respect to the traditional industry methods. This is because in some instance beforehand with Marc Jansard, we learned that there are also 3D printers for metal.
Okay, metal. Yes. So today we spoke about the plastic printer, the plastic production printers, and yeah, HP has also a metal printer, but I think it's something. I'm not an expert either, so it's something that we can maybe discuss in another session, because yeah, in metals it's a completely different story.
Okay, thank you. Then another question is whether you can explain a little bit about the overall ecosystem in order to produce these parts. That is to say, where is the design, what is the software that is used to design these parts and then finally produce them and check them. Can you explain a little bit about it?
Yeah, but it's a difficult question because the design, it really depends. There is not a software. There is not one way of designing. Each customer is using different methods. There are several softwares today in the market that you can use to design with 3D printing and to do topology optimization, for example, but there are several designs. So what usually happens is that we talk with, when you go into a new customer that they don't know 3D printing, you go with and have the first conversation and explain what is 3D printing. We explain some of these examples and which are the possibilities, no? And then the next phase is on first identifying which parts would it make sense to change to 3D printing because of cost, because it's low runs, because you want to optimize the design, because the time to part is critical. So there are several reasons why you would move a part that you are producing today in traditional to additive manufacturing. So this is very critical to understand really what is the pain point, and that you can also identify the pain point with traditional so that you can satisfy it with additive manufacturing. And then the next phase is in the redesign if needed. And in most cases it is needed. You can see, for example, this type of parts, as I was saying before. No, before it was identifying that there was a problem that the assembly was super long with metals, but then also it was the exercise of redesigning the part. And this is, as I was saying, there are several softwares. Each designer can use their own designs, but it's super critical. And then from there you send it to you have the design in different formats as well. You have 3MF, you have STL, you have several ones, and you would send just the file to the printer and with to the bucket. You need to do the bucket. This is the size of the bucket, and you can print the same part or several parts in the same bucket, and then you would just print and follow the end-to-end that Marc was explaining before. I hope I answered the question.
Yes, you were very helpful. We have another question, which is asking about the durability of the latex sheet that you were showing beforehand, and whether the technology has been used to see the resilience of making brake shoes with this type of technology.
Mm-hmm. Yeah, the durability is so this is a real project with some luxury car brands. So durability has been tested and it works. So this is already also one important thing here is that we've done a lot of research on the type of lattices to use. So durability depends a lot on the type of lattices. So here there was a very big project on which is the optimal lattice to work with this specific project of car seats. And then also you were asking about the footwear, no? This is
well, Maria, these are the brake shoes, those pads that cling on the disc for the automotive industry. Was that used for that parts, substituting? No. Okay.
No.
But if you want, please explain the part that you were mentioning then.
No, that I thought you were asking about the footwear parts. And here, for example, let me go one sec. We have an example of an application also in footwear. You can see this part here, the midsole is 3D printed. All the outsole part is normal produce, but this part is 3D printed. And this is also to optimize with the type of lattices and material to have a higher comfort or a higher energy return. Okay, these are for example, another very interesting application.
Thank you very much, Maria. I think now we are ready for the closure. I don't have any more questions in the Q&A box. Therefore, I would like to share the last slide where I'm going to go through the closure. Mm-hmm. Okay, thank you very much, Maria.
Okay, thank you.
Bye-bye.
Bye.
I'm going to go through to the last slide. This is therefore the closure of this webinar. It was a pleasure for me at the IET to have you here. Special thanks to Marc Jansat, the section manager of the R&D in HP Barcelona, and also to Maria Tauler, product marketing manager, who explained to us the applications and material. And of course, it is a great pleasure to have learned a little bit more about this particular technology. I hope the session was interesting and informative, and we look forward to have you more time in this type of events. So I wish you a very good day, and I wish you to see you soon again in this type of events. Bye-bye, and see you soon.